Okay, so I guess prepared to present myself as today's speaker. I will try to explain well, something I learned about Quillen's approach to rational homotopy theory. So I will start from just a very general idea of what we're trying to do and how it is related to what we studied all this semester. So first, the idea behind any sort of rational homotopy theory is to give an effective algebraic characterization of rational homotopy category of topological spaces, or simplicial sets if you want. So there are two notable approaches, one of Taroian and another one of Quillen. I guess Taroian's approach is more, well, it's a bit more elementary, so I guess it's a bit more popular. Usually when doing rational homotopy theory, the first thing that comes to mind are minimal algebras and stuff like that. And Quillen's approach via differential graded Lie algebras is a bit less common, but nevertheless, it's quite powerful. I hope that I'll be able to show it with just one simple calculation. Okay, so the basic idea of Quillen is that if we start from, I will use his notation. So this is a category of simply connected topological spaces. Then we can, first of all, make a replacement, and to replace a simply connected topological space by a reduced simplicial set. So we take a singular simplicial set of a topological space, and then apply this functor E2, which takes a special subset, which is formed by those simplices which have trivial faces in dimension 1 and 0. So, of course, we're considering pointed topological spaces and pointed simplicial sets. So faces in dimension 0 and 1 should be just this designated point. And so we arrive to the category which is denoted by this curly S2, which means one reduced simplicial sets, or I'm not sure, maybe I should call them two reduced, but it means that there is nothing in dimension 0 and 1. And in the opposite direction, we just take a realization, and obviously we get a simply connected topological space. Okay, then we move on to another category. So we take, well, loop group, loop simplicial group of a reduced simplicial set. It has an explicit description, but I'm not sure that I want to do this now. So, but the idea is that you basically shift your simplicial set by 1. So you decrease the degree by 1, and you generate free groups and impose some relations. So there is a bit of hurdle to introduce the correct face maps, but the idea is that it is sort of a free simplicial group generated by simplicial set. And so we arrive to connected simplicial groups. So they're one, I guess, yeah, they're one reduced, meaning that there are only trivial zero simplices. So the group in dimension 0 is just the trivial group. Okay, so that's pretty standard. Here we take in one direction the loop group, and in the other direction the looping or classifying space of a simplicial group. Okay, and now we can move on to get more algebraic categories. So this is all sort of geometric, and then we can move on to more algebraic stuff. So now we get another pair of adjoint functors. So we start from connected simplicial groups, and then we can take in one direction the group ring of a simplicial group, which is completed in the powers of its augmentation ideal. And in the other direction, so yeah, we arrive to simplicial complete Hopf algebras, which are also one reduced, since the initial group was one reduced. And in the opposite direction, we take a group of group-like elements inside of this Hopf algebra, and we arrive again at simplicial groups. Then we can move on to the next category. So in one direction, we take primitive elements of simplicial complete Hopf algebra, which gives us simplicial Lie algebra, also one reduced. And in the other direction, we take a universal enveloping algebra of a simplicial Lie algebra, and then we complete it in the powers of the augmentation ideal as well. Yeah. So yeah, I guess yeah. So this is still not very amenable to calculations. I mean, no one really wants to work with simplicial Lie algebras. So we pass from simplicial Lie algebras to differential graded Lie algebras using the monoidal Dalt-Kahn correspondence. So here we take normalized chains, and here we take an adjoint functor, and we arrive to the category of one reduced differential graded Lie algebras. And finally, using Chevalier-Eilenberg complex and another construction, which I'm not going to describe in this talk, but this, well, relatively, well, maybe I will give a short explanation right now without too many details. So we arrive to differential graded coalgebras, which are additionally two reduced. So I guess this thing is pretty clear from the talk on Dalt-Kahn correspondence, which Yegor gave last Friday. And about this pair of functors, I will just very briefly describe the general idea. So if we have just a Lie algebra, forget the gradient of the differential for a moment, then we can take its Chevalier-Eilenberg complex, which is just the external algebra on the dual of this Lie algebra, with a differential which comes from the Lie bracket, and how we do that? Well, if we have a Lie bracket, then really we have a map from external square of this Lie algebra into the Lie algebra itself. By taking duals, we get a map from G star, which is just lambda 1 of G, into external square on G star. Well, formally speaking, it's this space, but we'll assume for a moment that the Lie algebra is finite dimensional, and therefore we get a map into this space. And of course, if we have such a map, then we can extend it to the whole external algebra just by applying the Leibniz rule and the fact that it should square to 0. So D is thus dual to the Lie bracket, and it defines differential on this well, on this compass, but since it's an exterior algebra, it is actually a co-algebra with co-multiplication, which is given by mapping an element into its wedge product with itself. So, yeah. Sometimes it will be 0. Okay, so that's the general idea on how to construct the sequence of functors. And basically what Quillen is saying is that this sequence of functors induces isomorphisms on homotopy categories if here we additionally localize in well, rational equivalences. So here, of course, we consider everything over rational numbers. And so the general idea is that we can obtain an algebraic model, which is an element here or here, by applying this sequence of functors to get it. And so let me formulate the main theorem from Quillen's paper, which states that, one moment. Sorry. Yeah. So, moment, yeah. So if we have a homotopy category of simply connected topological spaces, then we can define a functor lambda from this category to the category of differential graded Lie algebras, which are one reduced, and then additional functor into the homotopy category of two reduced differential graded coalgebras. And these functors allow for computation of rational homotopy groups and rational homology, which means that lambda induces an isomorphism between homotopy groups of the space and homotopy groups of differential graded Lie algebra, where additionally this is not only an isomorphism of cube vector spaces, but actually an isomorphism of Lie algebras. So of course, here you have to shift by 1, and then you have the Whitehead bracket on homotopy groups. And it turns out that this bracket is compatible with the Lie bracket, which is induced on the homotopy groups of differential graded Lie algebra. Well, I'm saying homotopy groups, but really it means that you have to take a cofibrillant replacement and take homology. And so since you take homology of a differential graded Lie algebra, it also has a differential, well, I guess just graded Lie algebra structure. And additionally, if we take homology of the space X, then the composition C tilde lambda induces an isomorphism with homology of corresponding coalgebra, and this is an isomorphism of coalgebras induced by so you have a coalgebra structure and homology, obviously induced by the diagonal map with coefficients and rational numbers, of course. And here you obviously have a coalgebra structure which comes from the coalgebra structure on this thing. Okay, so that's the main theorem of one of the main theorems of Quillen's paper. But actually, well, speculatively speaking, this work on rational homotopy theory was one of the motivating factors behind the theory of model categories. And so actually we can state another powerful result, namely that actually all these equivalences which were, well, almost all of these equivalences which were stated above can be promoted to equivalences of model categories, with one notable exception. So T2, of course, is not a model category in any sense, because it is not even finitely complete. Because you can, for example, take a loop space as a limit of an appropriate diagram where each object is simply connected, and the loop space will not be simply connected. So, of course, T2 is not a model category. However, all other categories can be easily endowed with the structure of model category. And then we state that this, well, I don't think that I should rewrite everything again, but everything starting from this point and up until here are actually Quillen equivalences of model categories. So so the long sequence of equivalences on homotopy categories can be promoted to a sequence of Quillen equivalences. And well, this is quite nice because it allows for some, well, pretty immediate calculations of rational homotopy groups and stuff like that. Okay, so I think that now I will just try to briefly explain how to prove this theorem number one. So the main tool that Quillen uses is well, certain proposition about an adjoint functors and when they induce an equivalence of homotopy categories. So it is sort of a mix of several results which were stated earlier in the term. So I guess the closest thing is, well, are some results about deformable functors. So basically, so let me state this proposition. So assume that we have two categories with weak equivalences, C1 and C2, and we have a pair of adjoint functors. So we assume the following, that first of all, assume that C1, S1, C2, S2 are categories with equivalences, meaning that the classes S1 and S2 are 2 out of 3 closed and contain all isomorphisms. Then or maybe don't assume that, because I mean, yeah, so in the original formulation, it looks like this. So S1 contains all isomorphisms of C1 if and additionally 2 out of 3 property. Second is that F is in S2 if and only if GF is in S1. So sort of the condition that G reflects weak equivalences. And the final condition is that we have what we will now, I guess, call a deformation. So we have a functor from C1 to C1 and a natural transformation from R to AD. Such that for any object X in C1, the maps are X to X and are X to GF are X are in S1. Then the statement is that the left derived functor of F exists and is quasi inverse to the functor G tilde, which is induced on the homotopy categories. So since G reflects weak equivalences, we can take the induced functor on homotopy categories, and we require the direct functor of F to be well, we do not require, we get that the direct functor of f is a quasi-inverse of G tilde, meaning that homotopy categories of C1 and C2 are equivalent. So that's the version which Quillen uses to prove theorem 1. It, of course, does not say anything about model categories, and for a good reason, because the category G2 is not a model category. Okay, so I guess we've seen plenty of similar statements before, so I will not prove it right now, or ever for that matter. But I'll like to talk in more detail about ways to understand why this statement is applicable in each of the cases in this long sequence of junctions, which we described earlier. So clearly, we have to prove that, well, it is almost immediate that all of these adjunctions satisfy conditions 1 and 2. So sorry, condition 1 is really about the category C1 itself. And so there, it's almost immediate that weak equivalences in all these categories satisfy condition 1, because they're usually described by the fact that they induce isomorphisms on certain invariants, such as homotopy groups or homology. And since isomorphisms are a class which is which contains all isomorphisms, obviously, and which satisfies the 3-for-2 property, when we pull it back via some invariant, the class of maps which induce an isomorphism on this invariant obviously also satisfies this condition. So usually the most interesting part is the third condition of this proposition. And so we actually need to find this deformation for each of the categories. And one of the key statements in Quillen's work is that in each of these categories, which I recall are, well, I guess the more meaningful cases are simplicial groups, simplicial complete Hopf algebras, simplicial Lie algebras, differential graded Lie algebras, and differential graded coalgebras. So there, the fact is that we can find this deformation, and usually it is by replacing an object with a weakly equivalent free object. So let me show how this works usually. So let's, for example, consider a category of simplicial groups. Then we can take, and yeah, let's assume that it is connected. Then we can take the completion of the group ring of this simplicial group. We arrive into simplicial complete Hopf algebras. And then we go back by taking group-like elements. So yeah, sorry, yeah, no, that's not really what I meant to say. Sorry. So what I meant to say is that if we have, sorry for that. So assume that we have a simplicial group. Then we have a free simplicial group, which is weakly equivalent to this simplicial group. How we construct one? Well, if we have a simplicial group, then we can take its delooping or classifying space, which produces a simplicial set. So it's simplicial set. Okay, and then we can take the loop group of this delooping, which does not produce the initial group, but it does produce a free group, which is weakly equivalent to this simplicial group. So we have a weak equivalence as desired. And similarly, we can produce a free replacement for simplicial complete Hopf algebras, simplicial Lie algebras, differential graded Lie algebras, and differential graded coalgebras. So the main idea is that we can always replace something by homotopically equivalent free object. I guess one can say that it is somewhat of a disadvantage of equivalence work because this construction is not always applicable, and the proofs of Quillen utilize this freeness of the replacement in an essential way in many places, which makes it a bit harder to adapt it to other situations. But in the case of these categories, it is very nice that we have that we always have such a wonderful free replacement of any object that we want. So, for example, if we take sorry, not necessarily. If we take a differential graded Lie algebra, then let's call it L. Then we can take its Chevalier-Elimner complex, and then we can take the adjoint construction, which is denoted by L, which consists of the primitive elements in the cobar construction of this coalgebra. And then what we'll get is again free DGL, which is weakly equivalent to the initial Lie algebra. And the similar trick can be performed for simplicial Lie algebras and simplicial complete Hopf algebras. So, for example, for simplicial Lie algebras, we just augment this construction by applying the functor of normalized chains and its adjoint. So we go from simplicial Lie algebras to differential graded Lie algebras. Then we apply this composition of L and C, and then we go back by taking the adjoint of the normalization. Okay, so that's the idea behind verifying this property number 3. So first of all, we need to construct this functor R, and it can be done in all of the cases by taking certain free object which is weakly equivalent to the initial. Another cornerstone of this theorem 1 is proven that on free objects we actually have a weak equivalence between, so the adjunction morphism is a weak equivalence. And once again, it utilizes freeness in an essential way. So we have the following 3 key statements. three key statements about junction morphism in equivalence. So assume that, so the first statement is that if G is a connected free simplicial group, then we have an equivalence on homotopy groups, which looks like this. So this equivalence is induced by the adjunction morphism. So this is a statement about groups, and basically it shows that this pair of functors satisfy the condition 3 of this proposition, which I stated above, and this means that they induce an equivalence on homotopy categories. Another thing is that if G is a connected free simplicial Lie algebra, then we have an isomorphism which looks like this. So we once again apply a pair of functors from this long chain of junctions, and we get an isomorphism on homotopy groups. And finally, if R is a connected free simplicial augmented associative algebra, and R hat is a completion and powers of its augmentation ideal. This means that we have an isomorphism which looks like this. So what's the idea behind the proof of this result? Well, basically, we use the fact that all of these objects are free to show that an equivalence on associated graded objects induces an equivalence on the objects themselves. So the main idea behind the statements. So if we have, for example, a group, Lie algebra, or an associative algebra, then on all of these objects we have canonical filtrations. So here a canonical filtration is given by the lower central series. Here the canonical filtration is given by the, once again, lower central series by now, but now they're taken with respect to the Lie bracket. So this commutator filtration. And here we have a filtration by powers of the augmentation ideal. I guess Quillen denotes it like this. So this R bar is the augmentation ideal of R. And the idea is that if we have such filtrations, then we have this black box known as Curtis's connectivity theorem, which asserts that these filtrations are homotopically exhaustive, so to speak, which just in the plain terms translates to the fact that if we take a large enough index in this filtration, then the homotopy groups vanish. So if R is large enough, then this is 0 for any Q. Well, of course, R depends on Q, you understand. Similarly, for Lie algebras, and similarly for associative algebras. So this is the statement of this black box theorem. And if we have this statement, it means that if there is an equivalence on graded objects, there is an equivalence on objects themselves. And to show that we have an equivalence on graded objects, well, basically, we just need to consider this component. Because freeness of the respective object implies that the whole graded object is a free object generated by this first component. So, yes, it would be fair to say that this holds for all of them. And from that, we derive that since we're working over a field of characteristic 0, and it means that taking free object commutes with taking homotopy groups or homology, which means that we actually have an equivalence on graded objects, which implies by this filtration argument that we have an equivalence on the initial objects. So that's basically the point of I guess the first chapter of Quillen's paper, that we prove that there is this replacement, and for free which is done by taking free object. And on free objects, we have this equivalence, which means that we have an equivalence of homotopy categories because we can apply this proposition of deformable functors. So that's the way to prove. That's the way to prove theorem 1. I mean, of course, it was not very detailed, but the general idea is like that. But of course, there are some interesting topological details which are not reduced to just showing that we have this equivalence of homotopy categories. We actually need to show something more. And so I guess sections 5 and 6 of rational homotopy theory and dedicated to showing compatibility of these equivalences with multiplications. So it's either a Lie bracket or co-multiplication on homology. And I guess the basic idea of how it's done is by carefully inspecting that each of the functors does not break the structure. So, of course, the first thing that we need to do is we need to pass from topological spaces, or I think it's quite trivial that when passing to simplicial sets, nothing breaks. But we need to show that actually, when we pass to simplicial groups, we preserve this structure. So so we pass from simplicial sets to simplicial groups, and we can describe the rational homotopy Lie algebra. Well, actually, I guess not necessarily rational. I think this result holds for integers as well, but since we're working over rationals, rational homotopy Lie algebra will do. So the result is that if we have space, then its rational homotopy Lie algebra can be identified with an image of this thing. So and this thing here coincides with the Lie algebra of primitive elements inside this B algebra. Well, I guess it's not just a B algebra, it's a Hopf algebra. So since omega x, or maybe since I'm already dealing with simplicial sets, it's better to write it like Gx. So since Gx has its own multiplication, this thing has both the Pontryagin product and the co-multiplication, which comes from the diagonal. So this thing becomes a Hopf algebra, and by taking primitive elements, we get a Lie algebra. And the fact is that actually this Lie algebra coincides with the rational homotopy Lie algebra. Then we can carefully inspect the relation between yeah, so then we have to inspect the relation between this Lie algebra and what happens to it when we pass to this complete Hopf algebra and then to Lie algebra, which models the space. So let me state the result. So first of all, if we have a simplicial complete Hopf algebra, then we have an inclusion from primitive elements into this algebra. And also we have another inclusion from group-like elements into this algebra. sorry, maybe that's not okay. That's not an inclusion. I'm sorry. That's just a map which is given by this. So J of sigma -1. Then we have the following diagram. So if we take the homotopy groups of primitive elements, we have an isomorphism induced by the exponent with the homotopy groups of group-like elements. And we have an inclusion here into homotopy groups of the whole simplicial complete Hopf algebra, and a map which, since this was an isomorphism, is also an inclusion from homotopy groups of group-like elements into homotopy groups of A. Okay, so then if we know this result, which is relatively straightforward to prove, we just have to check it on, well, on the sort of on the generators. So we have to check it on spheres, and then we can expand it to all simplicial complete algebras using co-base changes and push out. Co-base changes and transfer composition. So if we have this result, then we have the following sequence, which is an isomorphism of Lie algebras. So we have an isomorphism of rational homotopy Lie algebra with the image of rational homotopy Lie algebra on the loops inside of homology of the loop space. Then this thing is isomorphic to image of homotopy Lie algebra on simplicial loop space inside of homotopy groups of simplicial Hopf algebra corresponding to this simplicial loop space. Then, since taking a completion does not change homotopy groups, as we sort of explained above, we can replace the thing on the right by its completion, getting a simplicial complete Hopf algebra. Then we can observe that we actually have, since the image coincided with primitive elements, we can take primitive elements of this simplicial complete Hopf algebra. And then, since the calculation of homotopy groups of some simplicial algebraic object really comes from taking the Moore complex, we get that it coincides with with homology of the Moore complex of this thing here. So by recalling that this functor lambda from a space to differential graded Lie algebra really was a composition of this sequence of functors. Well, I mean, we of course do this on homotopy categories, so that's why we write here the left-derived functor. And so this n tilde and p tilde and g tilde denote the descent of corresponding functors onto homotopy categories. And so since lambda was this thing here, we get that the homotopy Lie algebra of a space is isomorphic to homotopy of lambda x, which means that this algebraic model preserves the Lie structure in homotopy of topological space. And similarly, one can show that if we take this algebraic model one step further, we will get something which preserves the whole product on homology. So h of c tilde lambda x is isomorphic as a coalgebra to h of x. Okay, so that's the sort of crude part of Quillen's paper, where it is explained that we indeed have such algebraic models, at least at the level of homotopy categories. So second chapter of Quillen's paper is dedicated to showing that we actually have an equivalence of model categories. And so the first thing that he does is that he explains that we can basically perform both field localization. So in chapter 2, section 2, section 3 are dedicated to explicitly describing left pulse field localizations of simplicial sets and simplicial groups in some multiplicative system inside of integers. So, of course, by modern standards, it's not very illuminating to do this all by hand, but actually what Quillen accomplishes is that he explicitly shows that, for example, so of course, when we do a left both field localization, weak equivalences are some new class, which are old weak equivalences plus the class S. I'm sorry, I have the same notation for the system and the class, so we just denote the class like this. So we just take this class of maps which induce an equivalence modulo, well, after localizing in this system, in this case, or more generally, if we take in left both field localization, just take any set of maps and we add them to old weak equivalences. We generate a class by taking 342 property, and we get a new class of weak equivalences. Cofibrations remain the same, and fibrations are taken as maps which have the right Lifton property with respect to all trivial cofibrations. So that's the very simple description of left both field localization. And of course, there we can describe what are fibrant objects, which is done by Quillen in great detail. So Quillen shows that in this category of simplicial sets which are localized in this system S, R means that we take the R reduced simplicial sets, so the simplicial sets which have no non-trivial synthesis below dimension R. So he shows that in this category, vibrant objects are Hahn complexes with S uniquely divisible homotopy groups. I recall that S uniquely divisible means that well, group A is S uniquely divisible if the canonical localization morphism is an isomorphism. So, for example, uniquely divisible groups are well, Q uniquely, sorry, not Q, the correct term is Z without zero uniquely divisible groups, otherwise known as Q vector spaces. So this is nowadays is done just by some general considerations where we say that vibrant objects in both field localization are local vibrant objects in the initial category. So this condition that some space has S uniquely divisible homotopy groups just means that it is S local. And so so this is the contents of section 2, and in section 3, Quillen does the same thing for simplicial groups. So there, he also shows that we can localize them in a multiplicative system inside of integers. And then he shows that this result about loop and deloopant functors, which induce equivalence between simply connected simplicial, well, two reduced simplicial sets and one reduced simplicial groups, can be promoted to an equivalence between such localized categories. So if we have on this side R reduced, I guess R plus one reduced simplicial sets, which are localized in this system S, then we can take the loops functor, the classifying space functor, and we will obtain an equivalence between simplicial sets and simplicial groups, which are reduced and localized in the same system. In particular, it means that if S is equal to the set of all non-zero integers, then we have an equivalence between Quillen equivalence between rational category of simplicial sets and rational category of simplicial groups. So this shows that at least one part of our sequence of adjunctions induce an equivalence of model categories. So what is done next? Basically, we develop a sort of theory on how to construct a model structure on simplicial objects in any category. So then section 4, Quillen endows this category, which is just a category of simplicial object in some category A with a model structure given that A has enough projectives and, for example, that for any projective P and just any object, this simply show Hom set from P to X is a Kan complex. So then we can endow this category with the structure of model category and even simply show model category, but it is not discussed. And then we can use this to give model structures to categories of simply show complete Hopf algebras, simply show Lie algebras, and this allows us to prove that this pair of functions between simply show complete Hopf algebras and simply show Lie algebras, which consists of taking the completed universal enveloped algebra and the Lie algebra of primitive elements, can be promoted to an equivalence of model categories. So that's the contents of part 4 of the paragraph 4 of Quillen's paper. Then in section 5, Quillen describes standard model structure on differential graded Lie algebras and differential graded co-algebras, and basically there are no surprises. So if you've seen, for example, model structures on DGAs, that's basically the same thing. So we assume that weak equivalences in both cases are just quasi-isomorphisms. For differential graded Lie algebras, we take vibrations to be epimorphisms about degree 0, and co-fibrations are given by left lifting property with respect to vibration, with respect to trivial vibrations. But actually, since it is a co-fibrantly generated model category, co-fibrations can be described as retracts of cellular maps. So cellular maps are just something that can be obtained by transfinite composition of push-outs like this. So this is a free Lie algebra on a complex concentrated in degree n, one-dimensional degree n, and 0 everywhere else. And this is a disk complex which has non-trivial components in degrees n and plus 1, and a differential which identifies them. And we take a free Lie algebra on that. And so co-fibrations can be described like that. And in differential graded co-algebras, we basically have a dual thing. So weak equivalences are, once again, quasi-isomorphisms. Co-fibrations are injections, and fibrations are something that have a right lifting property with respect to trivial co-fibrations. Although I don't think that we can give such an easy characterization of fibrations, since the notion of vibrantly generated model category is not really a thing. And yeah, it doesn't work like that. But at least we understand how to give model structures in both cases. And then it is fairly routine to check that the adjoint functors between two categories induce inequivalence. Okay, so I think that this is it for this theoretical, so to speak, part of Quillen's paper. Now, let me briefly describe some topological implications of existence of such a theory. So, of course, for example, if we have Sullivan's theory, then it allows us fairly easily to compute homotopy groups. And as it turns out, actually, here we can do pretty much the same thing. So I think that in conclusion of my today's talk, I'm sorry if it's a bit shorter than usual, I'll just explain how to compute one of the, how to compute homotopy groups in one of the cases. So assume that we have two spaces which are simply connected. Then if X and Y are suspensions, then we have the following theorem due to Hilton, that if we take a wedge of these spaces, then we have a homotopy decomposition of this wedge as a product of, this loop space on a wedge as a product of loops on the first space times the loops on suspension of a wedge of B with the following infinite wedge. So here we take a smash of B and n-fold smash of A. So that's a purely homotopical decomposition which holds over the integers. However, in rational category, we have a simplification of this result. So if we take the homotopy Lie algebra of this thing, then we have a presentation of it as a co-product of homotopy Lie algebras of omega x and omega y. So the existence of such decomposition actually follows from purely from the existence of these equivalences between model categories of rational model categories of if you want rational category of simplicial sets of two reduced simplicial sets and differential graded Lie algebras. So we have a decomposition like this, and actually we can apply it, for example, to computation of a wedge of homotopy groups of a wedge of spheres. So if we take, for example, if we take Sn and Sm, and we want to understand how would look the homotopy groups of the space, then what we need to do is we need to just take the Lie algebra on the loops on Sn and take the co-product with the Lie algebra on the loops of Sm. And since this thing here is just a free Lie algebra which is generated in degree n-1, and this is a free Lie algebra which is generated in degree m-1, Then what we'll get is a 3D algebra, which is generated in degree x n minus 1, x in degrees n minus 1 and m minus 1. And actually, this result is a particular case of the following more general spectral sequence, which can be deduced for homotopy groups of cofibration. So assume that we have a cofibration. Then there exists a Lie algebra spectral sequence of homological type, which looks like this. So its E2 page is a co-product of Lie algebra on the loops of Y with Lie algebra on the loops of the cofiber, and it converges to the Lie algebra on the space X. So, of course, the previous case is just a particular instance of this result. So if we actually have a cofibration like this, then it splits as a co-product and the spectral sequence collapses, and we just get that the homotopy groups of the wedge is the same as the co-product of homotopy groups of each of its factors. So that's one application of this theory in topological context, but actually we can give another one. So we also have there is a Lie algebra spectral sequence which goes from free Lie algebra on loops of the reduced homological algebra of X to homotopy groups of loops on X, which is just the rational homotopy algebra of X. And additionally, we have another version which states that there is a, well, in a sense, it's a dual version, which states that we have a spectral sequence which goes from free graded commutative algebra on rational homotopy groups over space, and it converges to homology of X, and this is a spectral sequence of coalgebras. Okay, I don't know, maybe that's a good place to stop, because I think that it more or less covers the principal ideas behind this theory and its some of its simplest possible applications. Of course, I would be remiss if I didn't point out that Sullivan models Zoo dual to Quillen models. So Kazoo duality allows one to pass from one operand to its dual co-operand, and from algebras over an operand to co-algebras of this co-operand. And basically what we do in this case, we pass from these co-algebra models of topological spaces to algebra models of topological spaces in the sense of Sullivan. So these theories are, of course, closely related. And I guess maybe it would be nice if someone gave a presentation on Sullivan's approach as well. Okay, I think that I will finish here. Are there any questions, comments, or maybe just general suggestions about this topic? Okay, if there are none, then I think they'll end here. And thank you so much for coming.